Have you ever wondered why the intersection of these two subspaces is a subspace, but the union is not? Or have you ever thought about what the union, intersection, and sum of two subspaces actually mean? If not, then this video is for you. Welcome back everyone. In this video, we will explore the union, intersection, and sum of two subspaces along with their properties. These are some of the most confusing or misunderstood concepts in linear algebra, primarily due to the difficulty in visualizing things. However, once you begin to visualize the subspaces, the reasoning becomes much more intuitive, leading to a stronger and more solid foundation. We won't just look at the mathematical interpretation, but we will also use visuals to enhance our understanding. So without further delay, let's get started. So these are some of the most confusing or misunderstood concepts in linear algebra, primarily due to the difficulty in visualizing these subspaces. However, once you begin to visualize the subspaces, the reasoning becomes much more intuitive, leading to a stronger and more solid foundation. So let's first start with union of subspaces. So let W1 and W2 be two subspaces of a vector space V. So vector V is an vector space and W1 and W2 are its two subspaces. So the union of these two subspaces will contain all the elements that are either in W1 or W2. Okay, it is mentioned either. Okay, either in W1 or W2. So the union intersection of subspaces is exactly same as union and intersection in set theory. So for example, we have a union of W1 and W2 subspaces. So it contains all the element U such that U either belong to W1 or it belong to W2. It should belong to one of them. It's not necessary that it should belong to both of them. It can, but it can belong to at least one of them. So for example, let us suppose W1 contains these two elements, W2 contains these two elements, then their union will contain all the elements in both W1 and W2. Okay. So also, union of subspaces is not guaranteed to be a subspace. So for example, if I take these two subspaces W1 and W2, then it is not compulsory that their union is going to be a subspace. It can be a subspace, it cannot be a subspace. So it will be a subspace if and only if one of the subspaces contained in another. So for example, let us suppose we have this subspace W1. Okay, let us suppose we have another subspace W2. So we can see that neither W1 is inside W2 or neither W2 is inside W1. So in this case, W1 union W2 is not a subspace, But if we take W1 subspace and W2 subspace is inside W1, then in this case W1 union W2 is a subspace. It is a valid subspace. We will see a few examples just in a minute. So it is saying that is not a subspace unless one is contained. Here it is mentioned one is contained in the other. So one of the subspace should be inside another subspace. So here we are given one example. So for example, we have this R2 vector space. So let us suppose the input vector space V is R2, that is the xy plane. Okay, and let us suppose the first subspace is x-axis. We know that any line passing through origin is a valid subspace, right? And let us suppose the W2 subspace is the y-axis. Okay, so now we will see that W1 and W2 both are subspaces of V, but their union W1 and W2 is not a subspace. So first of all, we need to see what all elements are there in W1 and W2, and before that we need to see what are the elements belonging to W1. So for example, here is that this is the vector space V. Okay, this is the vector space V, which is R2, right? And this x-axis this x-axis is our subspace W1, right? This is our subspace W1. So uh, this is our subspace W1, right? and this is our subspace W2, that is the y-axis. Okay, now we will see these vectors, the blue vector, the red vector behind the blue vector, this yellow vector, all these vectors belong to the subspace W1. That is, all the vectors lying on the x-axis belongs to W1. And what type of vectors belong to x-axis? It it is of type this x comma 0. Okay, where x is any real value, right? So all such vector x comma 0 belong to W1, right? So for example, this red vector is nothing but 1 comma 0, right? And what all vectors belong to W2? It is of type sorry, it is of type 0 comma y, where y belong to R, right? This type of vector 0 comma y belong to the subspace W2. So for example, this purple vector, this belong to W2, this green vector belong to W2. So this purple vector is nothing but 0 comma 1, right? So we can see that all the vectors belonging to the subspace W1 lies on the x-axis and are of type x comma 0, and all the vectors belonging to the subspace W2 are lying on the y-axis and are of type 0 comma y. All right. So what all type of vectors belong to the union of W1 and W2? It either belong the vectors either are of type x comma 0, or it is of type 0 comma y. Only these two types of vectors belong to the union, right? Only these two types of vector belong to the union, because union will contain all the elements from W1 and W2, right? Union will contain all the elements from W1 and W2, right? Now for example, if we need to show that W1 in this case W1 and W2 is a valid subspace, so we should show this thing. So for example, let us suppose two vector u and v, let us suppose these two vector belong to the union W1 and W2, then their linear combination alpha time u plus beta time v should also belong to W1 and W2. If this is true, then only it's a subspace, right? Because we know that there are two property for a subspace, that it should contain the null vector, which is trivial. All these subspaces, subspaces contains a zero vector because all of them are passing through origin. So this is trivial, so no need to check it. But the second thing is that that the linear combination of any two vectors. You take any two vector from that subspace, their linear combination should be in that subspace. So let us suppose we take these two vectors u and v. U and v are any two vectors from the subspace W1 union W2. So if we are taking any two vectors, then their linear combination should also belong to the subspace, right? Now we can relax for now. We are relaxing this condition. So let us suppose we are taking alpha and beta as 1. If we are taking alpha and beta as 1, then we are saying that the vector u plus the vector v should belong to W1 and union W2, right? That is, here we are saying that it should close under vector addition, closed under vector addition, right? We are saying that it should close under vector addition, as it is mentioned that it should close under vector addition, right? But is it closed under vector addition? No. Why? For example, we take these two vectors. So let us suppose this is vector u, and let us suppose this is vector v. All right. So what is the sum of u and v? The sum of u and v is this. The sum of u and v is this, right? Which is nothing but u plus v, right? This is the sum of these two vectors u and v, which is 1 comma 1. So is it lying in the union? No, it is not lying in the union. Why? Because this u plus v, the u plus v is of which type? This u plus v belongs to the vector x comma y type, but the union w1 and union w2 doesn't contain these type of elements. It only contain either x comma 0 or 0 comma y. It doesn't contain the elements of type x comma y. That is w1 union w2 doesn't contain, it doesn't contain, or I can say that the vector x comma y doesn't belong to w1 union w2, right? Therefore I can say that the vector u plus v also doesn't belong to w1 union w2. So it is not closed under vector addition. So if it is not closed under vector addition, therefore I can say that uh, in this case w1 union w2 is not a subspace. It's not a subspace. Okay, so in the intro of this video, I mentioned that these two subspaces, the union of these two subspaces is not a valid subspace, right? So we will see that right now. So let us suppose this red plane is our subspace W1. Let us suppose this is our subspace W1 and this blue plane is our another subspace W2. Let us suppose we take two vectors, in the union. So let us suppose this vector u, it is belonging to w1. So it is also belonging to the union of w1 and w2. Right. Now let us suppose we take another vector, this vector, right? So this blue vector, or let me just draw it using the white color. So this blue vector, so let us suppose this is v, this belong to w2, so that means this also belong to the union. Now if you see the uh, linear combination of these two vector lying in the red plane and the blue plane, then the linear combination of these two vector is lying outside both this plane. This is u plus v. Okay, this is u plus v. Okay, so we can see that the u plus v is not lying in the union. So in this case, this vector u belongs to w1, which basically implies that vector u also belongs to w1 union w2. The vector v belongs to w2, which basically implies that vector v also belong to w1 union w2, right? So both u and v are belonging to the unions. Both u and v are belonging to the union. So their linear combination, that is u plus v, should also belong to w1 and union w2, but we can see that it is not belonging to w1 union w2, right? Why? Because the elements in w1, the elements in w1 belong to this type, that is x comma y comma 0, the z component is 0, belong to the subspace w1, whereas the element belonging to subspace w2 are of this type 0 comma y comma z, right? Okay, but u plus v is of this type, that is x y 0, and such type of value element doesn't belong to the union. They doesn't belong to the union. So here we can see that in the case of 3D also, the union of these two subspaces is not a subspace. Okay, now we will see the third case. In the third case, if you see, this is our subspace W1. Okay, and let us suppose this green plane is our subspace W2. I use this vector. Okay, this is u, and let us suppose I take another vector. I take another vector, this one. Let us suppose this one. All right. Let us suppose this is v. Okay. Now their linear combination will lie somewhere here. Their linear combination will lie somewhere here. Okay. That is u plus v. So if you see the vector u, it is belonging to the union of these two subspaces, right? The vector v, the vector v is also belonging to the union of the subspaces, and if you take their linear combination, that is u plus v, then it is also belonging to the union of the subspace, right? Why? In this case, the reason being that w1 is a w2 is a subset of w1. Okay, in this case w2 is a subset of w1. W2 is contained by w1. W2 is contained by W1. So no matter what two vectors you take, if you take any two vector, because W2 is inside W1, now you take any two vector, they will always belong to W1. So this is the Venn diagram. So this is W1 and this is W2. Now irrespective of what two vectors you take in the union W1 union W2, they will always belong to W1, right? That is true. And if two vectors belong to a subspace, we already know that W1 is a subspace. Okay, it is given because it is given. So W1 is a subspace. It is a subspace, right? It is a subspace. So if it is a subspace, then the linear combination of any two vector, that is, if we take two vector v and u belonging to W1, then any linear combination alpha times u plus beta times v will also belong to W1, right? So in this case also, you see, you take any two vector, whether it belong to W1 or W2 or the union, it will always belong to W1, right? Because W1 is the bigger subspace which is containing W2. So their linear combination will also lie in W1, and we know that W1 is a subspace, so it will preserve the linear combination. So that's why that's why this is the condition. If you need to check whether the union of two subspaces is a valid subspace or not, you only need to check whether one of the subspaces contained by another or not, or basically if one subspace is a subset of another subspace. Okay, so in the first example, W1 and W2, none of them are subset of each other, right? So in this case, the union is not a subspace. Same goes for the second case. Here also W1 and W2, they are not contained by each other. So again, the union here is not a valid subspace. But in this case, W2 is contained by W1. Okay, W2 is a subset of W1. So therefore, in this case, W1 union W2 is a valid subspace. Let's begin with intersection of subspaces. So, uh, intersection of subspaces. Let us suppose we are given two subspaces W1 and W2, and these two subspaces are of V. So it is saying the intersection of subspaces contain all the elements that are common to both. It is saying both W1 and W2. So it is same as the intersection of two sets we have studied in set theory, right? So intersection of two subspaces is same as intersection of two sets. So here it is given in the roster form that the intersection will contain all the elements U which belong to both W1 and W2. So if W1 contains these two elements and W2 contains these two elements, then their intersection contains the common element. Okay, so for example, this is W1, okay, and this is W2. So this is the intersection. So the intersection, that is W1 intersection W2, is a subspace. So one important thing we should notice, in union, the union of two space can be a subspace or cannot be a subspace. So we have seen two examples where it is not a subspace, and we have seen one example where it is a subspace. But the intersection is always a subspace. Now, why it is always a subspace? We first need to prove it, right? We need to prove that it is always a subspace. So let us suppose we take two elements. Okay, we take two element x and y belonging to the intersection of the two subspaces. So we have taken W1 and W2. Uh, let the vector x and vector y belongs to the intersection of W1 and W2. Okay, so uh, for W1 intersection W2 be a valid subspace, the linear combination of any two vectors, the linear combination of any two vectors should also belong to W1 and W2. That is, the linear combination alpha times x plus beta times y should also belong to W1 intersection W2, right? And if we relax this condition and if we take alpha beta as 1 for simplicity, then this basically implies that the vector sum, that is x plus y, should belong to W1 intersection W2. That is vector sum is closed or should be closed under intersection, right? We have seen that vector sum is not closed. In this case, vector sum is closed, but in these two cases, vector sum was not closed. You can see that vector sum is going outside the union. We need to prove that the vector sum is closed under intersection. And if we prove that x plus y belong to the intersection, then it can generalize for any alpha and beta. Okay, so it is given that x and y belong to the intersection. So if x and y belong to the intersection, then I can say that x belong to W1 and y also belong to W1, right? Because if you see this diagram, if you see this diagram, this is the intersection. I am saying that x and y belong to this intersection. X and y belong to this intersection. So if x and y belong to this intersection, then x and y belongs to W1 and x and y also belong to W2, right? X and y also belong to W2. Why? Because x and y belong to the intersection. We know that W1 is a subspace. It is given that W1 and W2 are subspaces, and we know the property of subspace that any two vector belonging to the subspace, their linear combination also belong to that subspace, right? So if x and y belonging to the subspace W1, then their linear combination x plus y also belong to W1, right? Similarly, if x and y belong to W2, then their linear combination also belong to W2. Why? This is because W1 and W2 are subspaces, right? Now, using these two things, using these and this, using these two things, we can say that it is saying that x plus y belong to W1 and x plus y belong to W2. So can we say that x plus y belongs to the intersection of W1 and W2? Right? Because here we are saying that the x plus y belong to W1 and it also belong to W2. That then this basically means that it is belonging to the intersection of the subspaces. So we begin our proof from this statement that x and y belong to the intersection, and we ended up here that their vector sum also belong to the intersection. So we have proved that for any two vector x and y which belong to the intersection of two subspaces, their vector sum also belong to the intersection of that those two subspaces. Okay, we have proved this that vector sum is closed under intersection, and this generalized for any alpha beta. You take any alpha beta 1 2 3 anything, then alpha times x plus beta times y also belong to W1 intersection W2. So therefore W1 intersection W2 is always a subspace. It is always a subspace. Okay, so let us suppose this is our first subspace, that is W1, and this is our second subspace, that is W2. Okay, so the intersection of two plane is nothing but a line, and in this case the intersection of these two subspaces is this green line, that is the y-axis. Okay, so this green line is the intersection, that is W1 intersection W2. This green line is the intersection, that is W1 intersection W2. Now let us suppose we take two vectors. We take two vectors x and y belonging to this subspace. This is the first vector. Let us suppose x. Okay, this is the vector y. Okay, so we can see that both x and y belong to the intersection. Both x and y belong to the intersection, and their linear combination, because both these vectors are lying in the same line, so their linear combination will also will be lying in the same line only. This vector is nothing but x plus y. Okay, so we can see that x and y both are lying in the intersection of the two subspaces, and their vector sum is also lying in the intersection. And you can prove for any x and y, right? Because the intersection is a line, and you take any two vector on a line, their linear combination will stay in the line, right? This is the property. This is the property which we have seen in our previous lectures a lot of time. So that's why the intersection is always a subspace. Okay, we have proved mathematically here that intersection is always a subspace. Why? because the linear combination will always remain in that intersection. So now I think it is clear to you that when I mentioned in the intro of the video that why the intersection of these two subspaces is a subspace, but the union is not a subspace. Now let's see sum of subspaces. So let's see, we have two subspaces, W1 and W2. The sum of subspaces is set of all vectors that can be written as the sum of a vector from W1 and W2. The sum of a subspace, the sum is all possible combination of two elements in W1 and W2. So it is saying all possible combinations. That is basically span. So basically you take two elements from W1 and W2, any two element, and you take their combination. That is linear combination. So the all the possible combination is sum. So for example, in this case, we are given the two subspaces W1 and W2. Okay, W1 is nothing but the span of 1 comma 0. That is all the vectors of type x comma 0. This subspace is x-axis, and this subspace is y-axis. That is all the vectors of type 0 comma y. Okay, so you take any two vectors, you take any two vectors from these two subspaces, then their combination belong to the sum. That is the combination belong to the sum of subspace. So, for example, we have seen this scenario in case of union, right? This is our W1 subspace, that is x-axis, and this is W2 subspace, that is y-axis. Okay. Now you take any two vector from W1 and W2. For example, I take this red vector and this purple vector. All right. So the sum of these two vectors will belong the vector sum of these two vectors. So for example, let us suppose this is vector x belonging to W1, and this is vector y belonging to W2. Okay, this is vector y belonging to W2. Okay, now you take the sum of these two vectors x and y. So this sum belong to the sum of the subspace W2. Okay, now you take another pair of vector. For example, this time instead of taking this blue and this violet vector, you take this blue and this green vector. Okay, this is the sum of these two vectors. Okay, now instead of taking these two vectors, let us suppose I take this green vector and yellow vector. So what will be the sum? The sum of these two vectors is will lie somewhere here. Okay, so this is the sum of these two vectors. So you take any two vector x and y, you take any two vector x and y, their linear combination is lying in R2. Okay, so the sum of vector space W1 plus W2, the sum is nothing but all the possible combination of any two elements in W and W2. Take any two element, you get a vector. That vector belong to the sum. Okay, in this case, the sum is nothing. The sum of these two subspaces W1 and W2, that is x-axis and y-axis, is nothing but the entire R2. So any vector in R2 is of type xy, and it can be written as the sum of it is nothing but a linear combination of 1 comma 0 and 0 comma 1, and these two vectors belong to W1 and W2, right? So in this case the sum is a subspace. So here W1 plus W2 is a subspace, right? W1 plus W2 is a subspace. Now there is one more property, just like we have seen in the case of intersection, that intersection is always a subspace. Similar to that, sum of two subspaces is also a subspace. So this is also true. So that sum is always a subspace. So now there is one special term called direct sum. So what is direct sum? So if the intersection between the two subspaces is null vector, for example, in this case the W1 and W2, the intersection in this case between these two subspaces is the null vector only. So in this case, such a sum is called direct sum, and it is denoted as, using this operator. Now there is one important formula. This is one of the most important formula for subspaces. It says that the dimension of sum of two subspaces is nothing but dimension of the first subspace plus dimension of the second subspace minus dimension of their intersection. So let us see. For example, in this case, what is the dimension of W1 subspace? It's a line, right? It's a line, so its dimension is 1. Okay. What is the dimension of W2 subspace? It is also 1 because it's just a line, the y-axis. And what is the dimension of the intersection? The intersection is nothing but 0. Therefore, the dimension of the intersection is 0 because it has only one element. It has just this point, right? So dimension is 0. So 0. So if you just simply add it, you get 2. And 2 is the dimension of the sum of W1 and W2 subspaces. And we can see this is true. Why? Because W1 plus W2 is nothing but R2. W1 plus W2 is nothing but R2, right? W1 and W2, W1 plus W2 is nothing but R2, and therefore the dimension of the sum of these two subspaces is 2, right? And we have seen using this formula also that the sum of these two subspaces is 2. The difference between sum of subspaces and union of subspaces. So union, when you are saying union, you are not taking any combination, you are not taking any linear combination, you are not considering. So here when I'm saying union of W1 and W2, I am saying take all the vectors in W1, take all the vectors in W2. Now that collection, so for example, let us suppose you have this collection which contains all the vector belonging to W1, and you have this collection which contains all the vector belonging to W2. Now you take the vectors, all the vectors from W1 and all the vectors from W2 and put it inside this box or this collection. This is W1 union W2. Okay, so we are not taking any combination between vectors of W1 and W2. No, we are just taking all the vectors from W1 and all the vectors in W2 and placing in another bag, and that bag is W1 union W2. Okay, and that's why in this case, this W1 and W2, that is x-axis and y-axis, the union of these two subspaces is not a subspace. Okay, because we are missing these vectors. We are missing the vector which is lying in the first quadrant or second or third or fourth quadrant. But in case of sum, we are already saying that we are considering the combination. Here, we are not only considering the vector lying in W1 and W2. Here, the diagram is something like this. We have vectors in W1, we have vectors in W2, right? You take the vectors from W1, you take the vectors from W2, you put them inside a bag, you put them inside a bag. Apart from this, you take a linear combination of vectors from W1 and W2 also, and you also put those vectors inside this bag. So W1 will contain all the vector on x-axis, W2 will contain all the vector on y-axis, but their combination, this sum which represents the linear combination, will contain all the remaining vector which are not in x-axis or y-axis, that is which are lying in these quadrants. So those are also included, and hence in this case the sum of these two subspaces in the entire xy plane, which is a subspace, right? So this is the key difference between sum of subspaces and intersection of subspace, union of subspace. So these two are very confusing because they look very similar. Okay, so that's all for this lecture. If you found this video helpful, then do like this video, subscribe to my channel, and also share with others. Till then, thank you. Bye.